Hi, I'm Xiaomao from Stanford University, and I'll be talking about my paper on knapsack approximation. So knapsack is a well-known problem, and in this problem you have n items. Each item has a profit and the weight, and you also have a knapsack with fixed capacity. So your goal is to find a set of items to fit into the knapsack, aka such that the total weight is not bigger than the knapsack capacity, and you want to maximize the total profit. And this problem is well known to be NP-hard. In fact, it is on COP's original list of 21 NP-hard problems. But since it is NP-hard, it is unlikely that there is a polynomial algorithm. This is why we are looking for approximation for exact case. So this is why we are looking for an approximation algorithm. So in the approximation algorithm, we want to find the solution that is accurate up to a 1 plus epsilon factor multiplicative, and in a time polynomial in both n and 1 over epsilon. So the knapsack approximation has been studied by top scientists since 1975. But despite the 5 decades of efforts, the best algorithm so far before our work still had a running time of 11 over 5, whereas the conditional lower bound has an exponent of 2. So we can see that there's a separation between the best algorithm and the conditional lower bound. But in our work, we saw a deterministic algorithm that achieves an exponent of 2. So in other words, we close this gap deterministically. And our algorithm actually took inspiration from techniques for subset sum. A subset sum is a special case of knapsack where each profit and weight is equal. And in another formulation, you're given n numbers and the goal and an approximation factor, and you want to find the set S such that the sum of items in S is epsilon close to the goal multiplicatively. And for this problem, Freeman and Knuckles have this perfect result from 2021, which basically states that the continental lower bound has an exponent of 2, and there's also an algorithm with the same exponent of 2. So we can see that for subset sum, there's really no gap between the best algorithm and the continental lower bound. So this is unlike the knapsack problem. So why is this the case? Why can't we find the algorithm for a subset sum, but we didn't for knapsack? This has something to do with the obstacle when it comes to approximation algorithms. And for simplicity, let's say we just want an additive error of delta as opposed to multiplicative error. And a natural thing we do for these kinds of problems is divide and conquer. Namely, we divide the problem into 2 subproblems, and we solve both problems and merge the answers. Since we are looking for additive error of delta, we also want to solve both problems with an additive error of delta. But this comes with our fundamental flaw. And to explain this flaw, let's just say we are adding 2 numbers together. And then let's say we are rounding both numbers down to the largest integer. And you compare those 2 summations, you can see that the error incurred, the error in the sum is equal to the sum of the errors incurred by rounding of each number. So in other words, the rounding error is going to accumulate. So since the rounding error accumulates, if we are doing divide and conquer and we are doing like an approximation of delta for both subproblems and then merge the answers, what we are going to get is an answer that has an error of 2 delta. So this is bigger than the approximation delta. But the reason why for subset sum, we actually have a perfect algorithm is that somehow scientists have figured out the way so that the rounding error does not accumulate. So in other words, it is kind of like a delta plus delta equals delta situation. So how is this possible? Freeman and Knuckles had this technique called delta specification. So the way this works is, given a set S of possible subset sums, we pick a set of pivots After picking the pivot, we want it to be the case that for each entry in the set S, the X in the set. So for each entry X, it is straddled by two pivots Y and Z. So one is smaller and one is bigger, such that the difference between X and Y and the difference between X and Z are both no greater than delta. So in the example below, you can actually see that for number 4, it is straddled by 2 on the left and 6 on the right, and the difference between 4 and 2, as well as 4 and 6, are both less than or equal to delta equals 4. So the core lemma that they show, or that they have shown, is that if you're doing a stratification of A into A tilde and stratification of B into B tilde, both with a factor of delta, then if you look at the sum set A plus B, each entry in the sum set is straddled by two delta closed summer pivots. So let's say you have this set A and you have this set B, and you look at the sum set A plus B. So you can you kind of just find all the summer pivots. For example, 5 here is equal to 4, which is the pivot from A, and 1, which is the pivot from B. And if you look at, let's say, the number 6 in the sum set, it is straddled by 5 in the left and 6 and 7 on the right. So that's basically what happens. And this is and there's a very beautiful thing going on here, which is you can see that A delta specifies to A tilde, there is like a delta error, and B is also a delta error. And then the running result is basically something delta closed, so it's also a delta error. So basically what happens is delta plus delta equals delta, namely the error does not accumulate. So since we have this kind of a thing for subset sum, a natural thing we can try for Knapsack is simply to adapt its specification idea for Knapsack. But it isn't so straightforward, because for Knapsack problem, instead of a set of subset sums, what we are dealing with is something called a profit function. And the profit function for a set S is defined so that S of a weight W is equal to the maximum total profit of the subset with total weight less or equal to W. And there's also this property where if you're taking the union of set A and B, then the power function of the union is equal to the max plus convolution of the power function of the two sets individually. So if we plot the power function on the 2D Descartes coordinate system, it's going to look like this, and this is the boundary between impossible weight profit pairs and possible weight profit pairs. And our idea for trying to find the specification for power function, just like how we did for sets of subset sums, is that we somehow pick a set of pivots, so that if we look at the specified function, which is obtained by just connecting the pivot with straight lines, then for every x coordinate, the difference between the y coordinate between the specified function and the original function is bounded by delta. And this is true everywhere. So in other words, the two functions are delta closed. And we want to achieve the same goal that Bima and Knuckles achieved in subset sum, which is basically if we are specifying a set A to A to A tilde and B to P tilde, and we also want A tilde plus B tilde to be close to A plus B. And importantly, we want to make sure that error does not accumulate, namely the delta error and delta error, the sum is still a delta error. So this here is a simple attempt that does not work. What will happen if we simply remove all the vertices A such that there exists the vertex B below A and the vertex C above A, and the y coordinate between those vertices are just no more than delta. And then we just keep removing all those straddled vertices and until we cannot remove anything else. So we call the remaining vertices pivots. So let's say we have this kind of a profit function. So we have this B, A, and C. So A is straddled by B and C. So we can just remove A. And after that, B and C becomes pivots. And the specified function is basically the connection between those two pivots. So what happens here is if we simply do a maximum product of the function with itself. The maximum product of the of the original perfect function looks like this, whereas the maximum product of the Spotify function looks like that. So we can see that there is a huge gap here between the two functions. So that means that this kind of a specification has an error bigger than delta, which means that it doesn't work. So our idea for fixing this problem is the observation that this kind of a bad scenario only happens if you have a concave structure. So if you look at the function on the left, we can see that for the middle point, the structure between it and the two red vertices is kind of concave. It's like a concave structure. So whereas if we have those convex structure instead, like shown here, then if you kind of do the same argument, then we can see that we are fine. Like if you are taking the maximum product between those two functions, it's going to look like the stuff on the right side, whereas the maximum product of the Spotify function looks like that. And we can clearly see that in this case, the difference between the Spotify function and the original function is bounded by delta. So there's a very simple modification of the attempt that didn't work before, which is we basically do the same thing, but we only remove A if the angle B to A to C is convex, like shown in the example on the left. So basically the angle P to A to C is convex and A is also straddled by B and C. That is the only situation where we can remove A. So what we can show is that if we simply do this instead of what we did before, then we can actually achieve the guarantee where where the error does not accumulate, basically. So the rest of the algorithm, that was the main idea of the algorithm. And for the rest of the algorithm, first we show that the specification actually makes the public function sparse in a sense. So if you have a public function that has a range 0 to m, then after a delta specification, the result is only going to contain m over delta alternating blocks of upper and lower convex halves. And moreover, it is also possible to merge two specified functions efficiently, because this kind of merging those kind of two functions is basically the task of convoluting the blocks of upper and lower convex halves. And if you want to convolute two upper or lower convex halves, this is something that can be done in near linear time using a monotone data structure that we show in our paper. And there are also several other minor ideas in the paper, and in the end, we can get our exponent of 2. So to sum up, we finally reached the theoretical optimal running time for Knapsack. And surprisingly, as we have seen, this is done by using two-dimensional geometry. But this still leaves us with some open problems. The first open problem is, let's suppose n is very small. So in this case, maybe we are looking for a running time of order n over epsilon. So is that achievable? There have already been some kind of partial progress towards this kind of a sparse case, first by Keller and Professor in 1999, and then by Chen in 2018. And if you look at exact knapsack, we also are kind of curious whether there is a running time that runs in that is of the form of n times W max, the maximum weight, instead of usual running time of n times the total weight or the subjective weight. And also for the case where n is very large compared to the weights and profits, is there a running time that is of the form n plus the sum of the maximum weight and sum of maximum profit to an exponent that is smaller than 2? So those are the open problems left for Knapsack. And that concludes my talk. Thank you for listening.